Good afternoon, everyone. How are you guys doing? I am also doing well, thank you, guys. So let's give another minute or two and see who will join us. And while we are waiting for more students to join us, I'm just waiting for our set of lecture slides to upload. So yesterday we talked about our own Milky Way galaxy. But for this lecture, we can now implement and use what we've learned with our own galaxy and figure out how other galaxies work. So for this lecture, we are going to look at the family of galaxies, measuring the properties of galaxies, the evolution of galaxies, what is the difference between active galactic nuclei and quasars, and then disk jet eruptions and galaxy evolution. So do you guys know this image? It's probably one of the most famous images in astronomy history. So this is the Hubble Deep Field image. So when Hubble was first launched, they took a spot besides the moon that with the unaided eye and with a few of the telescopes we have seems like there's nothing extraordinary going on. They pointed Hubble towards that area, and all of these dots you can see are galaxies that we can pick up, except this bright star in the foreground. But the rest are all galaxies, which is quite amazing. So, at the end of this lecture, we need to answer the following 5 questions. Number one, what are the different types of galaxies? Two, how do astronomers determine distance, size, luminosities, and masses of galaxies? Three, do other galaxies contain central supermassive black holes and dark matter, as does our galaxy? Four, collisions and interactions affect the evolution of galaxies? And lastly, how did supermassive black holes in the galaxy nuclei form, evolve, and affect their host galaxies? So when we look at galaxies, and this is a hint for the exam, these are the 6 main types of galaxies that we have. We have got spiral galaxies, irregular galaxies, spiral, peculiar, elliptical, and lenticular. So when we look at sci-fi movies, we can go in, jump in our spaceship, and explore the galaxy. But even in science fiction, you don't see different people exploring different galaxies because that is with extremely difficult to do with the technology we have and maybe will develop. But that's just something interesting on a side note. So when we look at different astronomy textbooks, they usually show pictures of spiral galaxies because spiral galaxies are usually the most beautiful galaxies to look at, and they features a lot of prominent features such as clouds of stars and gas and dust, and very beautiful to look at. So here we can see these different types of galaxies. So a century ago, photos of galaxies looked like spiral clouds of haze, and modern images of these relatively nearby galaxies reveal distant, beautiful objects filled with stars plus clouds as gas does. So we can classify these different galaxies. And this classification was developed by Edwin Hubble in the 1920s. So in this course, we haven't talked about Edwin Hubble much. So what other work was Edwin Hubble famous for? And the Hubble Space Telescope is named after him. Any ideas? Hubble proved the expansion of the universe, and that is universe is expanding today, known as the Hubble constant. But these different galaxies are classified the following way. So one, many galaxies have no disk, no spiral arms, and almost no gas and dust. And these are called elliptical galaxies, and their letter is E, class E. And it range from huge giants to small dwarfs. Then number second, we get disc-shaped galaxies, usually have spiral arms and contain gas and dust. And some of these spiral galaxies, so class S, have a central region shaped like an elongated bar and are called barred spiral galaxies. So E, elliptical, S is spiral, and then SB is spiral barred galaxies. So you learn in chapter 12 that a Milky Way is a barred spiral galaxy. And a few of these galaxies contain relatively little gas and dust, and these are lenticular galaxies. And lenticular are classified as S0. And then finally, notice the irregular galaxies as class I, which are generally shapeless and tend to be rich gas and dust. So it is surprisingly difficult to figure out what proportions of galaxies are elliptical, spiral, or irregular. In catalogs of galaxies, about 70% are spiral, but that is misleading because spiral galaxies contain hot luminous stars and clouds of ionized gas that make them easy to notice. And most ellipticals are fainter and harder to notice. Small galaxies such as dwarf ellipticals and dwarf irregulars are actually very common, but they are hard to detect. From careful statistical studies, astronomers estimate that ellipticals are actually more common than spirals and that irregulars make up about 25% of all galaxies. So how many galaxies are there? So long exposure images from small areas in the sky are called deep fields because they detect the most distant galaxies in deep space. So like we discussed our different stars, the temperature of stars, luminosities, fusion in their cores and different properties, so does the different galaxies have properties as well. So the one main property we can measure by galaxies is its distance. So the distance to galaxies are so large that it's not convenient to measure them in light years, parsecs, or even kiloparsecs. Instead, astronomers use a unit of megaparsec. So 1 megaparsec equal roughly 3.5 years across. So to find distance to a galaxy, astronomers search amongst its stars, nebulae, and star clusters for similar objects whose luminosity they know. Such objects are called distance indicators because they can be used to find a distance to a galaxy. Astronomers often refer to them as standard candles. If you can find a standard candle in a galaxy, you can judge its distance. And that is what we talked about yesterday. Shaped variable stars are reliable distance indicators because their period is related to their luminosity. The period luminosity relation has been calibrated, so you can use the period of a star's variation to find its absolute magnitude. Then by comparing its absolute and apparent magnitudes, you can find its distance. So, you guys know which space vehicle or telescope this is? Yes, that is the Hubble Space Telescope. So one thing that the Hubble does is it looks at the shaped variable stars, and these shapes are not visible in galaxies much beyond 30 megaparsecs. So astronomers search for less common brighter distance indicators and calibrate them using nearby galaxies that contain both indicators. For example, by studying nearby galaxies with distance known for shapes, astronomers have found that the brightest globular clusters has absolute visual magnitudes of about -10 and found that globular clusters are more distant galaxy. You would assume that the brightest of the globular clusters has absolute magnitudes of -10 and use that information to calculate distance. So astronomers can calibrate type 1a supernovae, those produced by the collapse of a white dwarf, because the white dwarf always collapses at the same mass limit. So the explosion reaches approximately the same maximum luminosity. So when type 1a supernovae occur in galaxies with distances that are known from Schur-Page variables and other distance indicators, astronomers can find the absolute magnitude of the supernovae at peak brightness. An example is shown in figure 13.4. When astronomers see a type 1 supernovae in a more distant galaxies, they observe the apparent magnitude of the supernova at maximum and compare it with the known absolute magnitude the supernova reach at maximum to find the distance to the galaxy. So in this image, we can see while dinosaurs roamed Earth, a white dwarf in the galaxy NGC 1309 collapsed and exploded as a type 1a supernova. And the light from that explosion reached Earth in 2002. So astronomers found shaped variable stars in the galaxy, so they can determine that it is 120 million light years away, and that allowed them to find the absolute magnitude of the supernova at its brightest. The supernova had faded from the view 3 years later, even though the second image was made using the Hubble Space Telescope. By comparing observations of many supernovae, astronomers have been able to calibrate type 1 supernovae as distance indicators. So now, since we have these calibrations, we can now set up a distance scale from the nearest galaxies to the most different galaxies. And we can use that scale. So the most distant visible galaxies are over 3,000 megaparsecs away, so 10 billion light years away. And at such distances, you see an effect akin to time travel. When you look at a galaxy that is millions of light years away, you do not see it as it is now, but as it was a millions of years ago. And when light began the journey towards Earth, so when you look at distant galaxy, you look back into the past by an amount called the look back time. The time in years equal to the distance in light years, the light from a galaxy traveled to Earth. So with look back time, we can use a better example. So how far is the sun away from Earth? That's 1 AU, yes. And if you put AUs in light minutes, it's 8 light minutes. So that means it takes light from the sun to reach Earth in 8 minutes. So that means we're seeing it 8 minutes ago. So if something happens to the sun right now, so for example, let's take a stupid example, the sun would completely disappear right now, then we will only notice it in 8 minutes. That is what we call the look back time. So is everybody familiar or happy with the explanation of look back time? Everyone happy? Awesome. So the next thing we need to take into consideration is Hubble's law. So although astronomers must work carefully to measure distances to a galaxy, they often estimate such distances using a simple relationship that was first noticed at about the same time astronomers were beginning to understand the nature of galaxies. And the most redshifts as they were receding, and the faintest galaxies had the largest redshifts. And in 1920s, astronomers Edwin Hubble and Moulton Emerson was able to measure distance to a number of galaxies using Schur-Page variable stars. And in 1929, they published a graph that plotted the apparent velocity of recession versus distances for their galaxies. So here we can see the Edwin Hubble and Moulton Emerson first diagram of the apparent velocities of recession and distance of galaxies that not probe very deeply into space, and the horizontal axis was later recalibrated. And this data did show, however, that galaxies are receding from one another. So the simple relation between the velocity of recession and distance is known as the Hubble law, and the slope of the line is called the Hubble constant. So the Hubble law is important because of its implications, and it is commonly interpreted to show that the universe is expanding. The distance to a galaxy can be found by dividing its apparent velocity of recession by the Hubble constant. And this makes it relatively easy to estimate distances to galaxies because a large telescope can record a spectrum of the galaxy and determine its apparent velocity of recession, even when it's too distant to have visible distance indicators. So Edwin Hubble's original measurement of H were too large because of calibration errors and his distance measurements. And the most precise modern measurements of H, the Hubble constant, yields a value of 70 kilometers per second per megaparsec, with an uncertainty of only a few percent. So once you find the distance to a galaxy from the distance indicators or the Hubble law, the next thing we can do is calculate the diameter and luminosity of the galaxy. So those are the next characteristics we can determine. So with a good telescope and the right equipment, you could easily photograph a galaxy and measure its angular diameter in arc seconds. And if you know the distance, you could use the small angle formula to find its linear diameter. If you also measure the apparent magnitude of the galaxy, you could use the distance to find its absolute magnitude and from that its luminosity. So all of that we can actually see what we've learned in previous lectures, now we are using again. So the results of such observations show that galaxies differ dramatically in size and luminosity. Irregular galaxies tend to be small, 5 to 25% the size of our galaxy, and of low luminosity, and although they are common, they are easy to overlook. Our Milky Way galaxy is large and luminous compared with most spiral galaxies, though astronomers know of a few spiral galaxies that are even larger and more luminous. So here is a reasoning of numbers, an example I can ask in the exam. So in this example, we have the apparent velocity of recession of the galaxy is called VR in kilometers per second and is equal to the Hubble constant, h, multiplied times the distance to the galaxy d in megaparsecs. So this is the equation. So it's VR equals h times d. So astronomers use this way to estimate distance from galaxies' apparent velocity of recession. So a good example I can give you is if a galaxy has a radial velocity of 700 kilometers per second, and the Hubble constant is 70 kilometers per second per megaparsec, then distance to the galaxy equals the velocity divided. Can you guys hear me now? Awesome. Sorry about that. Seems like there was connection issues on my side. So let me start sharing the screen again. You can see the slides, but I can't see the slides. That is very weird. Okay, I'm going to try and share the slides again. Okay, can you see the slides now? Awesome. So to find the mass of the galaxy is probably one of the most difficult things to do, but it's also a very, very important quantity of a galaxy that we need to find. So although there are few ways to estimate the mass of a galaxy, the most direct measurement uses Kepler's third law of planetary motion. You use that law to find the mass of binary stars. So if astronomers can measure the radius of a galaxy and the velocity with which it rotates, they can easily find the orbital periods of the stars as they orbit the galaxy. And then they can use Newton's versions of Kepler's third law to calculate the mass of the galaxy. So the most accurate of these studies involve observing the rotation of the galaxy at different distances from its center and drawing a graph called a rotation curve of the galaxy. So this is usually how a rotation curve will look like. So the most accurate of these readings of the most accurate, okay, I can go to the next slide. So measuring the masses of galaxies reverse two things. The first thing is the range of masses is wide. It can range from 1 million times smaller than Milky Way galaxy to about 50 times larger. And secondly, galaxies contain dark matter spread throughout extended galactic coronae, just as does our own Milky Way galaxy. So one last region remains to be explored, and that is what lies in the center of galaxies. Our Milky Way galaxy contains a 4 million solar mass black hole at its center. So do all galaxies contain similar objects? So with our understanding and where we are today, we know that all galaxies contain supermassive black holes in the center. And that is where the most mass of the galaxy is also usually in, but that's also what keeps a galaxy together. And then that brings us to another interesting concept, and that is dark matter galaxies. So given the size and luminosity of a galaxy, astronomers can make a rough guess as to the amount of matter it should contain. They only know much light stars produce, and they know how much matter there is between the stars. So it's quite possible to estimate the mass of a galaxy from its luminosity. But the measured mass of a galaxy is generally 10 times larger than the estimated from what is visible. So this must mean that nearly all galaxies contain dark matter. So X-ray observations reveal more evidence of dark matter. So X-ray images of galaxy clusters show that many of them are filled with very hot, low-density gas. The amount of gas present is much too small to account for the dark matter. Rather, the gas is important because it is very hot and its rapidly moving atoms have not yet leaked away. So evidently, the gas is held in a cluster by a strong gravitational field.
And to have a high enough escape velocity to hold the hot gas, the clusters must contain much more matter than what astronomers can observe directly. The detectable galaxies and the Coma cluster, for instance, amount to only a small fraction of the total mass of the cluster. So here we can see the gas in a cluster has a temperature of 100 million Kelvin. So what does this mean? So another way to detect dark matter goes back to 1916 when Albert Einstein described gravity as the curvature of space-time. So the presence of mass actually distorts space-time, and that is what you feel as gravity. He predicted that a light beam traveling through a gravitational field would be deflected by curvature of space-time, much as a golf ball is deflected as it rolls over a curved putting green, and that would result in twice the deflection predicted by Newton's theory of gravitation. That effect has been observed and a strong confirmation that Einstein's theories are correct. So another way we can that dark matter has and dark matter galaxies is in the effect of that we call gravitational lensing. Are you guys familiar with gravitational lensing? So gravitational lensing is very interesting. We can see gravitational lensing with other galaxies, dark matter galaxies, and also stars with high mass. So what it actually means is, or what is actually happening, let me get something to draw with. Here we have Earth on this side. So here we can see is Earth, I'm coloring Earth in, but there is a different galaxy over here. But now there is also a galaxy in between. So we cannot observe the galaxy behind this one directly because this one obstructs its view. But something interesting happens. If we take our telescopes and we, for example, look here and we look here, we can actually see this galaxy at the back because the gravitational force of this galaxy is so large, it actually distorts and bends light. So the light, instead of going this way towards us, it's now being bent around the object. So when we point our telescopes towards here and towards here, we can actually see the galaxy at the back that obstructed. And the same principle accounts for stars as well. We call that gravitational lensing. You guys happy with that explanation? Someone wants me to explain this again, or is everyone happy? Yes, you would be able to see the whole galaxy. So we can see the whole galaxy or only a distorted light. We actually see the whole galaxy. So we are actually seeing the galaxy as it were, example over here and here, but it's not actually physically here. It's just its light that's being bent around the galaxy in the forefront or the dark matter galaxy in this case. So no light is lost. It's literally just light being bent. So that is actually very, very cool, right? So it's not cut in two. So when you look in this direction over here, you would see the full galaxy on this side. And if you look this way around here, you will see the full same galaxy, so the exact same galaxy on that side. No, it wouldn't appear blurry at all or anything. You would literally just see the galaxy in that location, but its light actually comes from over here. So if you look at both spots, yes, you'll be able to see it simultaneously. That is, so literally, if you looked at this direction, you will only see one galaxy. If you look at this direction, you'll only see one galaxies. But these two galaxies will look exactly the same because you're actually looking at the same galaxy. And that is what we call gravitational lensing. So due to this gravitational lensing, it provides us with a clear evidence that dark matter galaxies are a real thing. So dark matter is not an insignificant issue, but observations of galaxies and clusters of galaxies show that nearly 90% of the matter in the universe is dark matter. And the universe you see, the kind of matter you and the stars are made of, has been compared to the foam of an invisible ocean. The dark matter remains one of the fundamental, unresolved problems of modern astronomy. So when we put Hubble's entire classification scheme together, these are the different galaxies we get. We have our elliptical galaxies, we have our spiral galaxies, and we have our spiral barred galaxies or barred spiral, and here we have our irregular galaxies. So how does galaxies evolve? So we've learned how stars evolve, and the same thing happens with galaxies. So considering the origin of our own Milky Way galaxy, presumably other galaxies formed similarly. But why did some galaxies become spiral, some elliptical, and other irregular? And an important clue to that mystery lies in the clustering of galaxies. So single isolated galaxies in the universe are rare, but instead galaxies forms in clusters and are clusters together. So these clusters can have a few upwards to a couple of thousand galaxies. And some of these galaxies have volumes of 10 to 10 megaparsecs across these clusters. So we get rich clusters that contain thousands or more galaxies, and mostly of them are ellipticals, and they are scattered through a volume of roughly 3 megaparsecs in diameter. And such a cluster is nearly always condensed. That is, the galaxies are more crowded near the center of the cluster. And at a center, such clusters often contain one or more giant elliptical galaxies. And then poor clusters are clusters that have less density. Not less density, less cluster, less galaxies inside them. So the Virgo cluster is an example of a rich cluster. It contains more than 1,500 galaxies and is 16.5 megaparsecs from our own galaxy. And a Virgo cluster, like most rich clusters, is centrally condensed contains the giant elliptical galaxy M87 at its center. So this is usually how these clusters looks like. But as one again, I talked about, we get poor clusters as well, and poor clusters usually contain fewer than 1,000 galaxies. So our own Milky Way galaxy is a member of a poor cluster known by the imaginative name the Local Group. So I don't know why, but astronomers named the cluster where our galaxy is in the Local Group. So here we can see the plane of the Milky Way, where our different stars is, and where we can look to different other galaxies. We have spiral, elliptical, and irregular. So the total number of galaxies in the Local Group is uncertain, but it probably contains 40 galaxies scattered irregularly through a volume roughly 1 megaparsec in diameter. And of the brightest galaxies, 15 are elliptical, 4 are spiral, and 13 are irregular. In general, rich clusters tend to contain 80 to 90% elliptical and A0 galaxies in a few spirals. In other words, galaxies that are crowded together tend to be elliptical or spiral, rather not spirals, but spiral poor galaxies. So they have a bit of a spiral, but it's not really there, rather than full-on spiral galaxies. So poor clusters contain a large percentage of spirals. Among the rare isolated galaxies that are not in clusters, over 80% are spirals. So somehow the environment around the galaxy helps determine its type. And astronomers suspect that collisions between galaxies are an important process. So one thing is also to realize is that galaxies can collide, and galaxies collide fairly often. So it's not in sci-fi movies where you have stars actually bumping into another. When galaxies collide, the different stars just generally pass in between each other and they form a new galaxy. So something to consider, the closest galaxy to us is the Andromeda Galaxy. And the Milky Way and the Andromeda Galaxy at some point in the future will merge to form even a bigger galaxy. So we have four new points and 3 new terms that we need to understand. So 1, interacting galaxies can distort each other with tides, producing tidal tails and shells of stars. They may even trigger the formation of spiral arms. Large galaxies can even absorb smaller galaxies, a process called galactic cannibalism. 2, interaction between galaxies can trigger rapid star formation. 3, evidence left inside galaxies in the forms of multiple nuclei and conflicting directions of stars and gas motions reveal that they have suffered past interactions and mergers. And then lastly, the beautiful ring galaxies are understood to be bullseyes left behind from high-speed collisions. So when we have 2 galaxies, they will have tidal forces moving to one another that can cause tidal and new star formation. And this is also a very, very cool process. So when we look at how galaxies are built, we need to eliminate a few older ideas. So it is easy to imagine galaxies normally evolve from one type to another, that you can call that a common misconception. But an elliptical galaxy cannot become a spiral galaxy, and an irregular galaxy becomes elliptical, contains almost no gas and dust from which stars are being made. So from this, we can see that elliptical galaxies cannot be young galaxies, but you can also argue that spiral and irregular galaxies cannot evolve into elliptical galaxies because spiral and irregular galaxies contain old stars as well as young stars. So the old stars tell you that spiral and irregular galaxies can't be young. The galaxy classes tell you something important, but a single galaxy does not change from one class to another any more than a cat can change into a dog. Another old idea was that each galaxy formed from a single cloud of gas that contracted and formed stars, which astronomers referred to the top-down hypothesis. So abundant evidence now indicates that large galaxies such as the Milky Way do not form primarily by top-down contraction, but instead by a bottom-up accumulation of smaller clouds of gas and stars. And the inflow of gas and the absorption of small galaxies is how it is formed. So you can read through these slides. It just gives more information about how these different galaxies are formed. But I want to jump ahead to active and galactic nuclei and quasars. So when we talk about the center of each galaxy contains a supermassive black hole. But sometimes those black holes are dormant and there's no matter falling into it. And in some cases, the black hole is very active and a lot of matter is falling into it. So when it is dormant, it is it has non-active galactic nuclei, and when it's active, it has an active galactic nuclei. So we can usually see this in the radio spectrum. So some galaxies are dubbed radio galaxies. And the active galactic nuclei, we abbreviate them as AGNs, and only a few percent galaxies are active. But their activity makes them especially prominent. For example, this is how a radio galaxy will look like. Here we can see the visible light, but if we look at radio, we can see there's a lot of radio emissions coming from it. So it all depends on how we observe the world. So this is a galaxy observed through different telescopes and different wavelengths. So here we can see visible light, infrared, and that one is a millimeter and submillimeter. This is radio, this is X-rays, and this is also X-rays with Chandra. So the first one of these active galaxies discovered was called the Seyfert galaxies, named after Mount Wilson astronomer Carl Seyfert. And he published a study of spiral galaxies observing at visual wavelengths. And Seyfert found some spiral galaxies have small, highly luminous nuclei with peculiar spectra. These galaxies are now known as Seyfert galaxies. And about 2% of spiral galaxies appear to be Seyfert galaxies. So Seyfert galaxies has a lot of infalling matter around them. And that also means they have very active centers. But there's also statistical evidence that Seyfert galaxies are more common in interacting pairs of galaxies than in isolated galaxies. And these clues hint that Seyfert galaxies may have been triggered into activity by collisions or interactions with companions, so companion galaxies. So you will find more such evidence as you study other kinds of active galaxies. So for example, this is what we call a radiolobe galaxy. So here we can see the center, and then we have these emitting lobes being emitted from the galaxy. And that is important because that brings us to specifically an active nucleus from a galaxy called a quasar. Have you guys heard about a quasar before? So quasar stands for a quasi-stellar object. You guys heard about quasars? Anyone heard about the term a quasar before? Okay, so quasars are an active galactic nucleus that's extremely active. And therefore, it emits a lot of radiation in the X-ray part and also the radio part of the spectrum. And what is weird about quasars is they are some of the most brightest objects we can detect with radio telescopes. So quasars are also a very cool object to study, and we can also use them as calibration sources to calibrate our telescope with. So one thing about quasars is that we've also realized is they have a very big redshifts. So that means that these quasars are very bright, but they are also very far away. So according to the Hubble law, these large redshifts imply very large distances. The first quasars studied were the brighter ones, but surveys have found many more. For example, the Sloan Digital Sky Survey discovered 90,000 quasars, and most of these quasars have very high redshifts and lie very far from Earth. So many quasar redshifts are greater than 1, and that may strike you as impossible. So remember, when you look at the Doppler formula, you cannot get a shift greater than 1. So the Doppler formula implies that such objects must have velocities greater than the speed of light. But the redshifts of the galaxies and quasars are not produced by the Doppler effect. As you will discover in the next chapter, the redshifts are produced by the expansion of the universe, and astronomers must use the equations of general relativity to interpret them. So redshifts greater than 1 are not a problem and merely indicate a great distance. So although the quasars are very far away, they are surprisingly bright. A typical galaxy at such a distance would be faint and extremely difficult to detect. But quasars show up on photographs as noticeable point of light. Apparent brightness and huge distance of quasars into the magnitude-distance relation, you will discover that quasars are ultra-luminous, having 10 to 1,000 times the luminosity of a large galaxy. So soon after quasars were discovered, astronomers detected fluctuations in brightness over times as short as a few hours. And those rapid fluctuations show that quasars are small objects, not more than a few light hours in diameter, so smaller than our solar system. So by the late 1960s, astronomers trying to understand quasars faced a problem. How could quasars be ultra-luminous but also very small? What could make 10 to 1,000 times more energy than a galaxy in a region as small as our solar system? Since that time, new large telescopes in space and on Earth's surface have revealed that quasars are often surrounded by hazy features whose spectra resemble those of normal galaxies. Evidently, quasars are located in galaxies. In addition, radio telescopes have revealed that some quasars are ejecting jets and inflating radio lobes. The evidence is now overwhelming that quasars are the active cause of very distant galaxies. In other words, quasars are the most extreme kind of active galactic nuclei that we can get. So you now know that many galaxies contain supermassive black holes at a center. And why do such objects produce eruptions and how do they form? So one thing that we know about this is we get these emanating jets emanating from the centers of these galaxies. So here we can see the supermassive black hole, an accretion disk of infalling matter. And here we have a relativistic jet and a shock wave. So the matter falling inward to the black hole spins very fast and becomes very hot. And it spins because it must conserve angular momentum. And as it shrinks inward, where it forms a flattened disk around the central black hole. Supermassive black holes have stronger gravity than stellar mass black holes and produce faster spins for the infalling matter and higher temperatures. So even a supermassive black hole is surprisingly small. So a 10 million solar mass black hole would be only 1/5 the diameter of Earth's orbit. So the matter can get close to the black hole and orbit very fast. So the infalling matter heats up because it picks up speed. And as it collides with other matter, those high velocities become thermal energy. That is, matter falling inward converts gravitational energy into thermal energy and becomes hot. So theoretical calculations predict that the high temperature puffs up the inner part of the disk and makes it thick. And even closer to the black hole, an orbiting particle is unstable and must spiral into the black hole. And the innermost part of the disk is empty and a black hole is hidden deep inside an empty central well. So further out, the disk is thinner and cooler. but the outermost part of the disk, according to calculations, is fat, cool torus of dusty gas. So astronomers can't see the black holes, but in some active galaxies, the Hubble Space Telescope can detect other parts of the central disk. So spectra reveal the speed of rotation, and Kepler's third law yields mass of the central object. And some supermassive black holes have masses of a few million solar masses, like the one in the center of our Milky Way galaxy, but the most massive contains billions of solar masses. So now we can put everything together and create our unified model of galaxies. So our unified model needs to explain to us how galaxies form and how galaxies fit together. So according to the unified model, what you see when you view the core of an active galaxy depends on how the black hole's accretion disk is tipped with respect to your line of sight. You should note that the accretion disk may be tipped at a steep angle to the plane of its galaxy. So just because you see a galaxy face on doesn't mean you are looking at the accretion disk face on. So the spectrum you observe depends on the angle of the disk. So if you view the accretion disk edge on, you cannot see into the central area at all. And you see lower temperatures and velocities. And if the disk is tipped so you can see the hot inner gas, you see higher temperatures and velocities. And if the disk is nearly face on, you would be looking directly into the central cavity, down the dragon's throat, as you can call it, and you would see extreme conditions. A few active galaxies have such extreme spectra. The unified model is far from complete, and the actual structure of accretion disks is poorly understood, as the process by which the disks produce jets. The unified model does not explain all the differences among active galaxies and quasars. Rather, it is a model that provides some clues to what is happening in active galactic nuclei. So putting this together, evidence shows that galaxies and supermassive black holes have evolved together. Astronomers can see this progression because at great distances to look back time is large, and observations reveal the universe as it was long ago. The masses of supermassive black holes are related to masses of the host galaxy's central bulges. In each case, the mass of the black hole is about 0.5% the mass of the surrounding central bulge. But there is no relation to the masses of disks of the galaxies. This reveals that the formation of supermassive black holes was connected with the formation of the central bulges. They formed and evolved together. So in the next chapter, we will start by looking at the universe and how the universe was formed. So now up until this point, we have done stars, we have done our family of stars, we have done the Milky Way galaxy, we have done how galaxies form, supermassive black holes inside a galaxy. So the next step is zooming out a little bit. And now determining, okay, the next bigger thing is the universe as a whole. We have a lot of galaxies in the universe, but how did the universe start? How old is the universe? And what will happen to the universe in the future? So that, ladies and gentlemen, is today's lecture. You have semester test week next week, so I won't be seeing you next week, but I will be seeing you the week after that. Otherwise, have a wonderful afternoon. I'll remain active if you have another question or two. Otherwise, good luck with your moon assignments and good luck with your next semester test week.